Are you able to see my PPT screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So yesterday we have just had a introductory discussion about this transport phenomena. So and today we'll start this subject, transport phenomena. So we'll start this subject with a basic fundamental, you can say fundamental property, which is called as a flux. And you will see that this is the backbone of any transport processes, flux. So this without this flux quantity, you cannot discuss heat transfer, you cannot discuss mass transfer, you cannot discuss momentum transfer. So this is the starting point of our subject, transport phenomena, flux. And you will see that this flux will come with you along the subject. In last class also we will be discussing about flux only. In first class also we are starting the subject with flux. So in last class also we will be discussing flux only. So anybody can give input. What is mean by flux? What do you understand by flux? Yeah, roll number 37, Vignesh. Yeah, can you tell me what is flux? Vignesh?
So am I audible, sir?
Yeah, you are audible.
So flux is nothing but any quantity passing per unit area in unit time, like
Very good, excellent. So many times what the people will have confusion, they will have confusion with the rate and flux. Flux is a rate per unit area. Okay, rate is a quantity per unit time. So you take any quantity. Okay, you take any quantity. So that is quantity per unit time is a rate, and rate per unit area is a flux. Now this is a generalized definition. Quantity per unit time per unit area. So quantity per unit time per unit area. So what will be the unit of flux in heat transfer? Roll number 47, Gurupreet.
Sir, I am audible?
Yeah. What is the unit of, what will be the flux in heat transfer?
Sir, joule per second per meter square.
Very good. Per meter square per?
Yes, per second.
Okay. And sometimes it is called as a watt per meter square. What is that?
Sir, it is like joule per second can be equal to the watt. Its
Very
power.
good. Excellent. And then how about in mass transfer, Somesh? Roll number 55.
Hello, sir.
Hi, tell me. What will be the flux in mass transfer?
Concentration upon meter square per second.
Concentration per meter square per second. Concentration, okay, quantity, okay, it will be concentration. So how to measure the concentration then? There are two ways to measure the concentration. Sometimes it will be measured in moles. Sometimes it will be measured in Somesh?
Yes, sir.
Yeah, sometimes it is measured in mole concentration. Sometimes it is measured in
I don't know, sir.
mass, kg.
Okay, sir. Mass.
You don't tell me you don't know. Okay, if you don't know, you should start your education with kg. These are not very high-fi questions and all. Okay, so concentration you cannot call it a concentration. It is a quantity. Okay, quantity is mass and or moles. Okay, that is not a concentration. Concentration is a moles per meter cube. Actually, concentration is a quantity per unit volume. That is general terminology. Now, if you tell that okay, you are calling this moles itself is a concentration, then it's fine. That is your terminology. No, nothing wrong in that. But we'll stick to a generalized nomenclature. So it is not a concentration. It is the amount that can be in mass or that can be in kg. Okay, kg or gram. Mass, okay, or moles per meter square per area. And now roll number 94, Saransh.
Yes, sir.
Saransh, yeah. What will be there in fluid mechanics? Flux.
Uh, Sir, considering the momentum transfer, we can say Newton second, which will be force into time, per unit meter square into second, which is area into time.
So
So it will be
what will be
Newton per
overall
meter square,
unit?
basically.
What will be? What is that?
Newton per meter square.
Very good, excellent. So Newton per meter square, that will be the flux, and that generally is termed as a stress. Okay, Newton per meter square, force per unit area, is termed as a stress in fluid mechanics. Okay, in general, applied mechanics also you have Newton per meter square, you have strength of material Newton per meter square, you have process equipment design Newton per meter square. So sometime it will be a you can say shear stress, sometime it will be a tensile stress. But in fluid mechanics, shear stress is a more dominating, okay, more dominantly used or more dominantly you can say involved in discussion. So shear stress in fluid mechanics is nothing but the momentum flux. So this is what the flux is. So heat flux is joule per meter square per second. Mass flux is a moles per meter square per second, and then momentum flux is a momentum per meter square per second. Momentum per second is nothing but the force. Okay, so Newton per meter square, Newton per meter square, that is the flux, momentum flux. So now as I told you in yesterday's class also, this transport phenomena is all about bringing this all subject together: heat transfer, mass transfer, momentum transfer. In fact, you can bring every transport processes. So whatever transport processes you can bring, that can be logically discussed and correlated with heat transfer, mass transfer, and momentum transfer. Say for example, I am discussing the moment of student in our department. Okay, moment of students in our department, or transport of student in our department. So what will be a flux? How flux can be defined if I am discussing transport of student in our department? Falguni, roll number 75.
So the number of students moving through unit area per unit time.
Okay, so per unit area, which area you will take?
Uh, so the area perpendicular to the motion.
Okay, so which area logically will be the better if you are discussing moment of a student in our department?
So the area, the cross-sectional area of the room through which they are entering, the wall in the
Wall.
direction.
No, they are not entering through wall, na?
Yes, so through the opening in the wall.
Yeah, opening in a wall is called as a door.
Door. Yes, sir.
Okay, so it will be a area of the door. Okay,
Yes,
so
sir.
number of student entering, okay, or moment of number of students per unit time, okay, per unit time, per unit area of the door. So this is what logically now you can correlate any transport processes. Okay, any transport processes. That is why we are studying this transport phenomena. Okay, so initially we'll try to understand how these heat transfer, mass transfer, and fluid mechanics are correlated to each other. They are very close to each other. Once we understood that, once we convince ourselves that okay, this heat transfer, mass transfer, and fluid mechanics, even though these names are different, but logically these are all similar subject, then what I can do, some of the fundamentals are very good studied in one area and can be used in other area, that you will see also. Okay, like molecular flux, understanding molecular flux or conductive flux in heat transfer is very easy. You can easily understand that molecular flux in heat transfer or conductive flux in heat transfer. But understanding same conductive flux in momentum transfer or fluid mechanics is very difficult. Okay, understanding only, that is not difficult to handle, even though it looks very simple equation, very simple. still fundamentally understanding how that is molecular flux. That is what the thing is there, and that can be understood very easily in heat transfer. Very easily you can understand conductive heat transfer in conductive heat transfer. Similarly, this conductive momentum transfer, it's very difficult to understand. So that is what we are going to see in today's class. So flux can be categorized into two classes. Okay, there are two classes of the flux. Logically, there are more than two classes, but you can say generalized class of the flux. There are two classes. Okay, two classes. One is a molecular flux, another is a convective flux. And you can see there is another class of flux in heat transfer. Okay, so that is called as a radiative flux. Okay, so a similar term nobody has coined it in fluid mechanics and mass transfer, radiative flux. But logically, we can correlate molecular flux in heat transfer, mass transfer, and momentum transfer. Similarly, convective flux. So these are the general class of flux: molecular flux and convective flux. This is well studied. So I think you might have spent heat transfer 1 discussing these two fundamentals only: molecular flux and convective flux everywhere. So roll number 71, Himani.
Yes, sir.
So what will be the molecular flux in heat? Molecular flux, definition of molecular flux. Or conductive flux. It is also called as a conductive flux. Conductive flux, convective flux. This molecular flux itself is a conductive flux.
So, molecular flux can be defined as the number of molecules crossing a unit surface in one direction during unit time.
No, that is flux. That can be molecular flux also, that can be convective flux also. What you are telling is a flux. Now, how to differentiate molecular flux and convective flux? Roll number 50, Rashmi.
Molecular flux is because of concentration gradient, like molecules go from higher concentration to lower concentration.
All the time concentration? Now here, that is what I am telling that. So we are discussing heat transfer, mass transfer, and momentum transfer together. So it will be concentration everywhere.
So we can say the potential gradient.
Yeah, gradient of driving force.
Yes.
Okay, and this flux is characterized by absence of bulk moment. There is no bulk moment in molecular flux or conductive flux. Okay, that is the flux taking place. Okay, this is what the definition is there. So the fluxes arising from potential gradient or driving forces are called as a molecular flux, and these are characterized by absence of bulk motion. Now, this is very easy to understand in heat transfer. If you consider heat transfer case, so molecules are not moving. Say copper rod was heated at the one end, and you can feel the temperature at another end. Copper rod, if you heat copper rod at one end, so you can feel the increase in temperature at another end. So and there it is purely a conductive flux, conduction. Heat transfer is taking place because of conduction. There is no motion of molecules. Okay, so molecule is at their same place. Only what they are transferring is they are transferring the heat energy. So one molecule take a heat energy and pass on the molecule to another molecule, and another molecule take a energy that will pass on molecule energy to another molecule. But molecule will not move, and which direction it will pass on? Where there is a potential gradient. Okay, potential gradient or driving forces are there. Okay, so here there will be a transfer of energy from lower temperature, higher temperature to lower temperature. So that is the conductive heat flux. Now same is case in mass transfer also. So as somebody told that, okay, the fluxes arising because of the gradient of concentration. Gradient of concentration is there because of that when there is a molecular that molecules are moving. Okay, molecules are moving because of a concentration gradient. Okay, but there is slight ambiguity here. So I am telling that absence of molecular bulk motion of the molecules is characteristic of molecular flux, but in mass transfer there will be always motion of the molecule. The mass transfer itself is a motion of the molecule. Mass transfer itself is a motion of the molecule. So I cannot say if there is no bulk motion, no mass transfer. So here we need to decide that if velocities are very, very small, that will be categorized into molecular flux or conductive flux in mass transfer. If velocities are very, very large, then we can neglect the bulk motion. Velocities not large, velocities are very small, we can neglect the bulk motion, and that will be characterized into molecular flux. If velocities are very large, then that will be characterized into a convective flux. And similar is the case in momentum transfer also. When there is no bulk motion, no bulk motion and flux is transferred, that time it is called as a molecular flux. Okay, this is molecular flux. Then what is the definition of convective flux? Roll number 30, Mani. Yeah, what is the definition of convective flux?
Convective flux is when there is a bulk fluid motion.
Very good. So can you give the example? So have you come across convective flux anywhere? Okay, anyway, I think you have studied couple of chapters in heat transfer in convective flux. So he has told exactly same thing. It is exactly opposite of the molecular flux. When there is a bulk motion, the fluxes arising from the bulk motion of the fluid. So bulk motion means the motion of molecule. Okay, molecules are moving here and there. So same thing. So air is heated up and air is moving up. Okay, air heated or boiling heat transfer, there also convection plays a role. Air heated and air molecules are moving. These molecules are moving, and because of this movement, this heat is moving from one place to another place. Okay, these molecules are moving. Molecules is taking a heat and they are moving from one place to another place. That is bulk motion. So bulk motion or bulk flow, they are called as a convective flux. So initially we will discuss a molecular flux, and then slowly we'll go to convective flux and interface flux. So anybody has any confusion over this molecular flux, convective flux, and a basic definition of flux? Any confusion? Okay, so which is the law which will govern a molecular flux in heat transfer? Roll number 13, Shiva.
Yes, sir.
Which is the law which will govern a molecular flux in heat transfer?
Sir, Fourier's law, I think.
Fourier law of
Sir, temperature gradient is the driving force, but I don't know the law.
So what is the Fourier law? You don't, this I know certainly you might have come across, and as you
Yes.
are in almost third year of the chemical engineering, you should know this. So you just don't give me excuse that you don't know. I will ask the question to you only when I am expecting that you are knowing the answer.
Okay, sir.
Okay,
Sorry.
just I want to check your understanding also, and if you want to excuse that you don't know, so that is not the good thing. At least you should try. And molecular flux, you might have done this 100 times, 100 times calculation on molecular flux. 100 times you might have heard of conductive flux. So 100 times you might have heard of that law also.
Yes, sir.
What is that conductive law of heat transfer? You told actually, initially itself you told. Roll number 40, Ravi.
Yes, sir.
Yeah. So what is the conductive law in heat transfer?
Sir, it is the Fourier's law, sir.
Fourier law of heat conduction. That name itself is saying that. Fourier
Yes,
law
sir.
of heat conduction. That is what a molecular flux, which will define the molecular flux in heat transfer. Ravi, can you tell me what is the conductive flux law in mass transfer?
Sir, it is fixed law.
Very good, very good. Fixed law of diffusion. Okay, fixed law
Yes, sir.
of diffusion uh, is a law which will define the molecular flux in mass transfer. How about in momentum transfer, fluid mechanics?
Sir, actually, I'm not able to remember it now.
Okay. So, have you heard viscosity?
Yes, sir. Yes, sir.
So, which law which will define the viscosity?
Sir, I'm actually remembering the formula, but
So, that is Newton's law of viscosity. Okay, that is
yes,
Newton's law of viscosity. So these are the three laws. Okay, first of all, in heat transfer, it is Fourier law of heat conduction. In mass transfer, it is fixed law of diffusion, and in momentum transfer, it is Newton's law of viscosity. So now today, and maybe in next class, we'll just try to concentrate on these three laws. This law already you studied, and in fact you are mastering this Fourier law of heat conduction. You might have solved hundreds of problems in Fourier law of heat conduction. You might have solved many problems in fixed law of diffusion. You might have solved many problems in Newton's law of viscosity. So studying this law is not our main aim in this couple of classes. Okay, what is our main aim in this couple of classes is to study how these three laws are similar to each other, because these are the basis of, you can say, Newton's law of viscosity is the basis of fluid mechanics. Almost 50% of the design parameters in fluid mechanics can be estimated, or can be you can say is based on a Newton's law of viscosity. Similar is the case in heat transfer, Fourier law of heat conduction. 50% of the design parameter in heat transfer is based on Fourier law of heat conduction, and 50% of the design parameter in mass transfer is based on a fixed law of diffusion. So this is 50% of heat transfer, mass transfer, and momentum transfer, which will govern by Newton's law of viscosity, Fourier law of heat conduction, and fixed law of diffusion. So certainly this three law which is given on your slide represent the 50% of mass transfer, 50% of heat transfer, and 50% of fluid mechanics. And now and that already you have studied. You have studied in detail Fourier law, fixed law, Newton's law. Now here in transport phenomena, our main aim is to understand how these three laws are similar to each other. Because they are already similar to each other. Scientists have proved that thing. Okay, now we will also see how they have proved, how they have logically correlated these three laws. Newton's law is similar to Fourier law, is similar to fixed law. So once we got convinced ourselves. Okay, now here the main aim of this couple of classes is to convince ourselves that heat transfer, mass transfer, and fluid mechanics are not a different subject. Okay, even though they looks different, but logically all these three subjects are similar to each other. That is what our main aim of this couple of classes, which we are going to cover in, say, today's class and say next class. It's a couple of classes we will try to understand how these three laws are similar. Otherwise I will be discussing this law. Okay, I will be discussing this law, and already you have studied this law. So that is not our main aim, to discuss that law. Okay, while discussing in this law, the cases are designed. Okay, the discussion overall, the language of discussions are designed in such a way that you will feel that you are just changing the areas. You are moving from fluid mechanics to heat transfer to mass transfer. Still it looks like a similar discussion three times we have done. And once we will get Newton's law of viscosity, then we will get Fourier law of heat conduction, then we will get a fixed law of diffusion. Okay, that is what our main aim is there. So we'll start with the Newton's law of viscosity. So cases are designed, okay, cases are designed in such a way that all these three areas, okay, to establish the similarity, between Newton's law of viscosity, Fourier law of heat conduction, and fixed law of diffusion. That is our main aim. Discussing this law is not, you can say, your main aim. Now, can you see this highlighter?
Yes, sir.
Yeah, this highlighter is visible to you, na? It is moving actually.
Yes, sir. Yes.
So whenever I am explaining something, so you should concentrate on this highlighter. So consider a case. So here case is there at time t less than 0. Okay, what is the case? So there are two plates. Okay, this is one plate, this is bottom plate, this is upper plate. There are two plates. So this is bottom plate and this is upper plate. So you can consider thin plate, metal plate or wood plate, anything, solid plate you can consider. These are the two plates. And this is my x direction. This is just a axis direction is given. So this is x direction and this is y direction. Okay, this is y direction, this is x direction. And at t less than 0, t less than 0 means my experiment is not started. T less than 0, time less than 0. So time less than 0 means I'm not in past. Okay, I'm not in past. Time less than 0 means my experiment is yet to start. My experiment will start at t equals to 0. Okay, my time at time t equals to 0, my experiment will start at time t less than 0. So, and this plate, the space between this plate, this distance between these two plates is y. So this distance should be smaller. So say you can say y mm. So y mm, and this is filled with some fluid. So you can take it water, fluid. The definition of the fluid is the material which can flow. So it can be filled with air, it can fill with water, it can fill with oil, it can fill with ethanol, it can fill with methanol. So any one fluid, it is filled with, this place is filled with a fluid of a viscosity mu. And at time less than 0, everywhere velocity is 0. Both the plates, okay, both the plates are steady. This fluid in this between two plates are steady. Everywhere velocity is 0. So velocity in x direction. So velocity in x direction means this direction velocity. There is no velocity in this direction, and this length of the plate in x direction is infinite. So length of the plate in x direction is infinite. Y direction, the distance between these two plates is finite and small. This y is finite and small. The distance y is finite and small, but length of the plate is infinite. This is at t equals to 0. And then at t equals to 0, okay, t greater than 0. So what is done? This is before start of experiment. After start of experiment, what is the difference? The bottom plate is given a force F. Okay, bottom plate is given force F, which will create a velocity V, constant velocity in bottom plate. Now this bottom plate is continuously moving, and this length of the plate, bottom plate is infinite, length of the upper plate is infinite. Okay, length of the bottom plate is infinite, length of the upper plate is infinite, and this as soon as it start moving, so this first layer of the fluid, say I am considering that it is filled with water, it is filled with water, Newtonian fluid, it is filled with water. The first layer of the fluid will attain a velocity v. As soon as it is started at t equals to 0, the first layer of the water in touch with the solid plate will attain a velocity v. Because the velocity of solid is v, the first layer of the fluid will have same velocity. What is this boundary condition is called as a roll number 37 Vignesh?
Boundary condition.
Yeah?
Initial boundary conditions.
Not initial boundary condition. Initial boundary condition. Look, I am telling that at time t equals to 0, this lower plate is given a force F. And because of this force, this lower plate start moving in x direction with a velocity v. Lower plate. Now, as lower plate is moving with a velocity v, the first layer of the fluid, which is in touch with this solid plate, will move with velocity v. What is this boundary condition? This is not an initial boundary condition. Here, roll number 35, Praneeth. Roll number 35, Praneeth.
Surface boundary condition.
Not surface boundary condition. Yeah, anybody else?
No slip boundary condition.
Okay. So whenever I'm telling anybody else, you should tell your roll number also, because I need to make a note. Okay, who is talking that no slip boundary condition?
So BT 1870.
Yeah, you can call it at only 70. Okay, 70 na?
Yeah, BT 18.
Okay, BT 18. Oh, very good. So this is called as a no slip boundary condition. So BT 1870. Okay, Darshan, very good. So Darshan is an expert in this actually. So this is called as a no slip boundary condition. So till now, many of you might have in concept that no slip boundary condition means velocity is 0. Okay, that is, I will say that it is misconcept. Okay, it is not a no slip boundary condition. No slip boundary condition means a layer of the fluid which is in touch with solid will have same velocity as that of solid. There is no slip between first layer of the fluid and last layer of the solid plate. This is called as a no slip boundary condition. So this, you remove that misconception from your mind that no slip boundary condition means velocity equals to 0. Okay, no slip boundary condition means there is no slip between a first layer of the fluid and last layer of the solid material. So any solid material and first layer of the fluid will have same velocity. If it is 0, it will be 0. If it is non-zero, then it will be non-zero. That is called as a no slip boundary condition. Now, according to no slip boundary condition, this is given a force F, but this is kept steady. Upper plate is kept steady. So upper plate is kept steady. This Vx equals to 0. This last layer of the fluid, which is in touch with the upper plate, will have 0 velocity. This is also no slip boundary condition. Okay, this is also no slip boundary condition. This is also no slip boundary condition. Velocity here, first layer of the fluid will have velocity v, last layer of the fluid will have velocity 0. Okay, so now what is happening? So after some time there will be some velocity profile in this plate, in this you can say distance between these two plates, there will be some velocity profile exist. So what is happening? Say see if I can draw. So consider this is my plate. So this is first molecule, this is second molecule, this is third molecule, this is fourth molecule, this is fifth molecule, and this is sixth molecule. This is seventh molecule, and this is upper plate. Okay. Now, according to no slip boundary condition, as this plate, okay, this plate is moving with a velocity v. This plate is moving with the velocity v. So this molecule will start with also moving with velocity v. Okay, and this according to no slip boundary condition. So this upper plate velocity equals to 0. velocity equals to 0. This velocity equals to 0. So certainly this molecule will have velocity equals to 0. This is also no slip boundary condition. This first layer of the molecule in touch with a plate having velocity 0 will have a 0 velocity, and this is the first layer of the fluid which is in touch with this plate having velocity v. It will have velocity v. So certainly, because of this mass of the molecule and this velocity, so it will have some momentum in this direction. Momentum will be in this direction, that is mass into velocity. And these molecules, second row of the molecule, are in touch with this first layer of the molecule with some molecular interacting forces, van der Waals force of interaction. So this second layer, so this will try to pull this molecule. This first layer of the molecule will try to pull this molecule in this direction. Okay. So this layer of the molecule, first layer of the molecule, so it will attain some v1 velocity. So then as it attains some v1 velocity, so this will try to pull this molecule. So this will have some v2 velocity. And similarly, as this plate is steady, so this molecule will have velocity 0. So it will try to keep this molecule 0. It will try to keep this molecule 0. It will try to keep this molecule 0. So there will be a, you can say, some force which is encouraging velocity which is coming from the bottom plate, and some force which is reducing the velocity which is coming from the top plate. And this will give rise to a flux. Now, what is the direction of the flux? Roll number 88, Pratish.
Sir?
Yeah, what is the direction of momentum flux?
Sir, from right to left. Like if we consider
X
the area, the
Y,
particles.
X or Y.
Sorry, sir.
Whether the momentum is flowing in X direction or momentum is flowing in Y direction?
X direction.
Huh?
X direction.
So there is X momentum. There is no Y momentum?
No, sir.
So there is actually molecular momentum is there only in Y direction. In X direction, it is a convective momentum. Okay, convective momentum is flowing in X direction, because there is a moment of molecule in X direction. But because of this moment, this molecule is trying to move in X direction. So this molecule has some X momentum. It will give some X momentum to this molecule, and it will also start moving in this X direction. So it will give some X momentum to this layer above, but there is a transfer of moment in Y direction. Okay, momentum is transferred from this one molecule to another molecule. Then this momentum is transferred from second molecule to third molecule. This momentum is transferred from third molecule to fourth molecule. This momentum is transferred from fourth molecule to fifth molecule. And this molecule is steady. So similarly, zero momentum is transferred from this molecule to this molecule, and accordingly there will be a flux of momentum in Y direction. And I am discussing molecular flux. Okay, this Newton's law of viscosity is discussing molecular flux. So molecular flux is there in Y direction. There is a momentum transport in Y direction, but which momentum is transporting? X momentum. Okay, because I have X velocity, so this momentum, direction of momentum is this. But this X momentum somehow is transported to this molecule, second layer of molecule. Again, it will attain X momentum, but this transport of momentum is in Y direction. Okay, transport of momentum is Y direction, and these molecules are not moving. Molecules are moving in X direction. Molecules are moving in X direction, but transport of momentum is in Y direction. Hence, it is called as a molecular momentum flux. Okay, so without bulk motion, so I am discussing the transport of momentum in Y direction, and there is no bulk motion in Y direction. There is a bulk motion, but it is in X direction. So effectively, there is no bulk motion in Y direction, and effectively there is a transport of momentum in y direction. Hence it is called as a molecular momentum flux or conductive momentum flux, because there is an absence of bulk motion in y direction. There is a bulk motion in x direction, so x momentum is transported in y direction. So x momentum is transported in y direction, hence this is called as a molecular momentum flux. This is very important. So why it is called as a molecular momentum flux? Okay, because there is no bulk motion. So no bulk motion, it doesn't mean that there is no flow. Flow is there in y direction. There is a momentum in y direction, but this is transported in x direction because of van der Waals force of attraction and other force of interaction. There will be other interactive forces between this molecule and this molecule. So momentum is transported in y direction, and this momentum is in x direction. Hence you will see that there are two directions associated with the molecular momentum flux. So there will be a tau yx. So first suffix indicates a transport of momentum, and second suffix indicates the direction of momentum. So anybody has any confusion in this? Why it is called as a molecular momentum flux? Even though there is a bulk motion in y direction, there is no bulk motion in there is a bulk motion in x direction. There is no bulk motion in y direction. This is clear to everybody? Anybody has any doubt? Okay. So what exactly will happen? What will be the velocity profile? Expected velocity profile? Can anybody judge what will be steady state expected velocity profile? Roll number 63, Shresh.
Yes, sir.
Yeah, expected velocity profile will be at steady state.
At steady state, it will be decreasing from bottom to top.
It will be decreasing from bottom to top, and if distance y is very small, then it will be a linear velocity profile. Okay,
Yes.
if y is very small as compared to x, okay, length of the plate, then certainly it will be a linear velocity profile. So you can see this is transient zone. Okay, this is transient zone at t equals to 0. At t equals to 0, only lower plate is moving and first layer of the fluid is moving. So at t equals to 0, this is my velocity profile. What do I mean by velocity profile? First of all, velocity profile is nothing but the, you can say, pictorial representation of velocity with location. So what do you mean by velocity profile? Velocity profile is nothing but the pictorial representation of a velocity with location, which will give me what a velocity profile will give me. Give me a location, I will give you velocity. That pictorial representation is called as a velocity profile. So here, so you can see what will be velocity profile at the 0. At 0, at y equals to 0. So this is y equals to 0 and this is y equals to y. So at here everywhere velocity is v at time t equals to 0. At time t equals to 0, so everywhere velocity is v, but at y, other than this, all layer will have velocity 0. Then slowly what will happen? So this molecule, okay, this molecule will have momentum. It will transport the momentum to this molecule. This molecule will transport the momentum to this molecule, and then what will happen? This slowly this momentum is transported, and this will be the velocity profile at time t equals to t1. Time t equals to t1, say 50%, 50% of the molecule got the momentum 0, momentum from this plate, and 50% of the molecule is yet to get the momentum. So here after velocity is 0. So from say y equals to y1 to capital Y, velocity is 0. So here velocity will be 0, and there will be slowly increase in velocity, and it will be maximum at the bottom plate. Similarly, at time t equals to t2, it will be penetrated to more distance till this point. You can say till this point, this is y2. So at time t equals to t2, so all the layers above this point will have velocity 0, and then slowly it will increase and will reach a maximum velocity equals to v at the bottom plate. That is at time t equals to t2. And at time t equals to infinity means larger time where steady state is achieved. Okay, larger time where steady state is achieved. That is the indication which is given by t equals to t infinity. T infinity means not infinite time. This is sufficiently larger time to attain a steady state. So at time t equals to t infinity, so this layer will have velocity 0 and this layer will have velocity v, and there will be linear variation of velocity with the y. So here at y equals to 0, velocity will be v, and y equals to capital Y, velocity is 0, and this will be the velocity profile. So these are the four velocity profile. Four velocity profile. First velocity profile as time t equals to 0. Second velocity profile at time equals to t1, time t equals to t2. All these are called as the transient velocity profile. Okay, these velocity profile are called as the transient velocity. Still steady state is not achieved. For simplicity, we will be discussing only the steady state. As yesterday also I told, everything in your subject is discussed steady state. We will be discussing everything about steady state. Everything about steady state in heat transfer, steady state in mass transfer, steady state in momentum transfer, and that too for laminar flow only. We want to make this subject as simple as possible. So here discussing this velocity profile is not so easy, because this is transient. This is variation is there with time. So certainly a partiality means partial differential equation is involved in that. Partiality is there. Partially you need to study physics, partially you need to study time also, because there is a variation with respect to location also, variation with respect to time also. So certainly partial differential equations are involved. So we are not interested in this for time being. We are interested in here only, where there is no variation with respect to time, only there is a variation with respect to location only, steady state. As there is no variation with respect to time, it is called as the steady state. So what Newtons have observed? So what Newtons have observed at this steady state, this is the observation made by Newtons. Newtons observed that force per unit area. This is force per unit area. Area is the area of this plate. This is force in this direction. This is called as the shear force. And area is the area of this plate. Area of this plate is length of the plate multiplied by width of the plate. Width of the plate is the width perpendicular to this plate is directly proportional to velocity gradient. So this is nowhere theoretically discussed. So initially this is the observation made by Newtons, and then he has given a detailed discussion over this viscosity, and complex equation is also given. We will discuss generalized law of viscosity after say 10-15 classes or so. Here Newton's law of viscosity. So this is the observation: force per unit area is directly proportional to velocity gradient, and this velocity gradient, this proportionality constant, it is called as the viscosity. So force per unit area equals to viscosity multiplied by velocity gradient, and same equation is written in differential form. Mu is a viscosity, and same equation is written in differential form. So that is, this force per unit area is written as tau yx. Okay, tau yx, that is equals to minus mu velocity gradient dvx by dy. This is a differential form of same equation. Now here, as I told, so all the time this momentum flux will be defined by two suffixes. Okay, so this is the difference. As I was telling that there is a similarity between heat transfer, mass transfer, and momentum transfer. But in momentum transfer, there are two directions associated with the flux. There are two directions associated with the flux. First one will be the direction of momentum itself, and second one will be the in which direction this momentum is transported. While in heat transfer, only one direction is associated with a flux. In which direction is heat is transported? In which direction this mass is transported? Heat doesn't have any direction, but momentum have a direction. Okay, so here we'll have two suffixes, and this is standard. So tau yx, It means that I have x momentum which is flowing in y direction. So I have x momentum, I have velocity in x direction, but this momentum is transported in y direction, and there is no bulk motion in y direction. So this suffix is very important. Tau yx and tau xy will have altogether different meaning, even though they are same. They are same, but physically they have altogether different meaning. Okay, so tau yx means I have x momentum. Okay, momentum direction is x, but this momentum is transported in y direction. I have explained you, so I think it is there. Yeah, this momentum is in x direction, but it is transported in y direction. So this is what tau yx is there. So this is called as the shear stress. So shear stress, and this is rate of strain. This is called as the rate of strain or rate of deformation or shear rate. So what is Newton's law of viscosity? Newton's law of viscosity is shear stress is directly proportional to rate of strain. So shear stress is directly proportional to rate of strain, and the proportionality constant is a viscosity. Shear stress is directly proportional to rate of deformation. Proportionality constant is a viscosity. Shear stress is directly proportional to shear rate, and proportionality constant is a viscosity. This is the Newton's law of viscosity. Newton's law of viscosity, and this negative sign indicates velocity is decreasing in with increasing y. So I want this flux to be a positive all the time. So why this negative sign is given? Negative sign is given because I want this flux to be positive all the time. There is no fundamental physical significance of negative flux. Okay, fundamentally it will be a positive flux means flux. So negative money. So it is you can call it as a loan as a negative money. Okay, but it will not have physical significance at all. Similarly, negative flux doesn't have physical significance at all. So all the time we'll try to keep this flux positive. All the time this will try to keep this flux positive. So hence here in this case, as velocity is decreasing, okay, velocity is decreasing. Here I will have maximum velocity. Here velocity is lower. Here velocity is lower. Here velocity is lowest. Velocity is decreasing and y is increasing. Y is increasing. So hence there is a negative sign. Say for example, take another case. If I instead of origin here, if I take origin here, and this is my y direction and this is my x direction. If my origin is at the upper plate and this is my y direction, this is my x direction, then tau yx will be plus of mu dvx by dy. Okay, it will be positive all the time. What will be my main aim? My main aim will be to keep this flux positive. So this is the Newton's law of viscosity. Anybody has any input related to this? Any doubt related to this Newton's law of viscosity?
Excuse me, sir.
Yeah, tell me. Roll number?
Sir,
Your roll number?
Roll number 103.
103. And name?
Saurabh.
Saurabh. Tell me, Saurabh.
Sir, like you said, there is a molecular flux, molecular momentum flux in the y direction and the convective flux in the x direction.
Yeah.
So, sir, this differential form of equation is like only for a single flux, right?
Yeah.
Sir,
This
but
is
there are
defining. This is defining. This is giving me that too only molecular flux. Molecular flux in y direction, x of x momentum. X momentum flowing in y direction in a way of conduction or molecular flux. Molecular flux of x momentum in y direction.
Yeah, I got that, sir, but why we are not considering that x direction flux too?
We'll consider one by one. We'll come to that also.
Okay.
We'll come to that afterward. So because here case is defined in such a way that this is more important for design purpose. Okay, there is so simply assumption added that viscosity is constant. Okay.
Right.
So, and if you go further, we'll go further in transport phenomena, then you will see that viscosity itself is not constant. There are non-Newtonian fluid also.
Yes, sir.
And laminar flow is there. We have considered laminar flow. Okay.
Okay,
For laminar flow only, this is true. For turbulent flow, it will vanish. This is not at all important for turbulent flow. For non-Newtonian fluid, this is not. This equation will not be true actually. So what is our strategy is, we'll start with a very simple thing. We'll understand this simple thing fundamentally, make ourselves clear in simple thing. Then we'll move on to complex thing. Once we have confidence that okay, I can understand, I have very good fluid mechanics, I have good heat transfer, I'm very good in mass transfer, then you can add complexity, whatever complexity you want. Steady state is also added. So straight away, if I say that I will study transient zone, and then I will show you the equation, which will be the full of the slide will be equation only. Then you will clear with this subject, and then you will say that transport phenomena is very difficult. So main aim is simplify the case as simple as possible. Try to study that and get the confidence that now I can study heat transfer. Now I can study transport phenomena. Then you can add one complexity into that, and slowly you can build whatever the complex design equation, whatever you want.
Got it, sir.
Okay. Anybody else?
Hello, sir.
Yeah, tell me. Roll number?
53.
63. Yeah, tell me.
53.
53 or 63?
53.
Okay, tell me. 53.
Sir, the first layer of above the bottom sheet, we are we are considering that from starting it is taking velocity v, right?
Yeah.
But why we are not considering that it may cause some friction in the bottom?
No. That is what no slip boundary condition is.
Okay.
That is what no slip boundary condition is there. So there is no slip between a layer of solid and a layer of fluid in touch. They will move with same velocity. Whatever you do, okay, whatever you do, they might attain this steady state in fraction of second, which is, you can say, not in scope of study of any of the equipment cannot catch that. You can take it as maybe you are thinking that maybe microsecond or say second raised to 10 raised to 100, that time might have been taken, but it is taking very small time, fraction of second. So within which this both layer will attain same velocity. That is what no slip boundary condition we are at. And you see, actually there will be so much assumption whenever you derive this model. Okay, this is called as a model equation. This is called as a model equation. There will be so much assumption in that. And this I will say also, assumptions are very important, very important to give the simplicity to your model equation. Your model equation should be as simple as possible. At the end, so whatever assumption you might have added, that will give you some error. And then at the end, you will design using model equation, and you will get a unique solution, because your model equation is a very simple equation. You will get a unique solution, design solution, and then you can add a factor of safety. See, using this, if I am adding, if I am calculating force required to attain some velocity and all, so at the end, what I will be doing, I will be adding 10% force more. So certainly I will be getting whatever I want, and that factor of safety. So that assumption should be logical. All assumptions should be logical. That is what it is assumed. No slip boundary condition. So we are not into that that smallest time level, and that will not hamper any design parameters. Okay, that is what. So we will take that as a no slip boundary condition. Okay.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Yeah. Anybody else?
Hello, sir.
Yeah. Tell me.
So, rule number 5.
Yeah. Tell me.
Yes, so I have a doubt. So if can the molecular momentum be significant enough to cause a movement along the y direction of the particles?
Yeah, turbulent flow is there, na?
Okay, sir. Okay.
Turbulent flow is that one only, na? That time we will have
Uh-huh.
movement of molecules in y direction also.
Okay, sir.
Hello, sir.
Yeah, tell me.
Sir, roll number 101. Sir, actually, I had a doubt that we assume infinite length of the upper and below layer.
Yeah.
So, what is the significance of that assumption? Does
So
it
this is
carry
just
that it is
assumed
a
to
finite?
derive this equation. Simple form of the equation. Okay.
Sir, but it was an observed equation, means as you told that Newton observed it.
Yeah. So if this distance is in mm, so this is set to mm, and this length of the plate is 1 meter.
Okay, comparatively infinite.
Don't you think that okay, this 1 meter is infinite
Yes.
as compared to 1 mm?
Yes, sir. Yes.
Yeah, that is what it is comparative.
Okay, so
Infinite.
if it is in the proportion, the equation may
No.
change.
Then you will not get a linear velocity profile. Then you will get a parabolic velocity profile. Non-linear. I don't know whether you will get a parabolic or something. Okay. Some non-linear velocity profile you will get if this plate is very far from this.
Okay.
Okay, then
Yes.
you will not get a linear velocity profile. Non-linear it will be. So somewhere at steady state also, so you will be getting somewhere like this. You will get some velocity profile. Okay.
Okay, sir.
Somewhere steady state will be attained, and you will get that velocity profile. Okay, then is it okay?
Yes,
So I'm
sir.
stopping here. So I will continue in next.